All right, so to do the electron and noble gas configurations, we need the periodic table. So I'll just be doing it directly on here. Okay, so we're going to be doing Ti first. Ti, I'm going to write it right there. And if you guys remember, we want to take a look at the subshells and the shells. Okay, so if you guys remember, this section right here is going to represent the S subshell. And I'll try my best to color code them. This section right here is going to represent the P subshell. And then this middle section, the transition metals, are going to be the D subshell. Okay, so the element that we are looking at is right here, titanium. So we basically need to get to titanium. Okay, so we're going to go with the first row. First row is going to be the 1s subshell. So we got 1, 2 electrons in there. So that's going to be 1s2. We got to go to the second row now. We got row 2, and that's the 2s subshell. And there's 2 elements we need to go through, so that's 2. Next, we have the 2p subshell, and there are 6 electrons there, so we're going to get through that. So 2p6. Next, right here is the 3s subshell. So there's 2 electrons there, so 3s2. Right here, we got 6 electrons again, so that's going to be 3p6. Last row, we got the 4s subshell, and there's 2 of them, so 4s2. And then titanium is the second in the D subshell area, so this one is going to be 3d2. Okay, so just keep that in mind. The only real tricky part is remembering that when you go to the D subshell, it's going to be just one number less. So I know this isn't the 4th row, but it's going to be a 3D subshell. Okay, so that's the electron configuration. Any questions on that part? All right, so I don't like this one. It's too much writing. And so instead, we're going to do the noble gas configuration. For the noble gas configuration, we're just going to look at titanium, and we are going to look at the noble gas that comes right before it. Noble gases are this last column right here. So Ti is right here. So if you just go backwards, the noble gas that it is closest with is argon. So instead of writing this long thing right here, we can just simplify it as Ar in brackets. And then we can just copy down the rest for S2 and 3D2. And that's it. That's the electron and the noble gas configuration. All right. Any questions about that first one for Ti?
Here today.
Morning. All right. So one quick thing I do want to mention, I was looking at some of the grading sheets for the AP test. Sometimes on the AP test, they'll give you a question where they ask you, hey, write the electron configuration. But when you look at the actual answer rubric, you can give, you're good, you can give either the electron or the noble gas. So you don't have to write out this long thing, even if it says write the electron configuration, you can just give the noble gas configuration and you'll still get full points, okay? I'm just teaching you guys how to write this whole thing because there are multiple choice questions where they'll give you the long ones and you just need to pick the right one. But when you need to write the electron configurations, you can just write the noble gas configuration. Okay? And for our test as well, if I ask you electron configuration, I'm totally okay with you guys just giving me the noble gas. Okay, save yourself some time. All right, so that's for Ti. We were also looking at Ti2 plus. Okay, now I'm not gonna do the electron configuration just because it's a lot of writing. But if you look, the only difference between Ti and Ti2 plus is going to be 2 electrons, right? Because it goes from neutral to +2, which means if Ti loses 2 electrons, it becomes Ti2 plus. And so we just need to take away 2 electrons from the electron configuration. Now, I mentioned it very briefly at the end of last class, but we always take away from the S subshell first instead of the D. So for Ti2 plus, the electron configuration or the noble gas configuration will be the brackets with Ar, and it'll be 3D2. And that's it. Okay, all we got to do is take away these 2 electrons. What's up? Sorry, what was that? Yeah, we take it out from the S subshell because it's 4s, it's actually a higher energy level. And so let me show you the chart. Or sorry, yeah, because just from a higher energy level, so that's where we just take away the electrons. It's just the way it works. Yeah. Yeah. It's just one of those little things you need to memorize. There is a longer explanation for it, but you don't even learn that until like physical chemistry, like upper div college classes. So unless you're going to major in chemistry, you're not really going to have to pay attention. Okay. All right. Any questions on the two? Okay. All right. So we're going to finish off by drawing the what is it? The chart, just so that we have one last piece of practice with it. We're not going to do it for all of it, but we'll just do it for TI just so that you guys remember. Okay. Actually, I guess we can do it for both. We haven't. It's going to be the same. Okay. So we're going to draw the chart now. So if you guys remember, we're going to be doing it for TI first. Now, we're going to start from the very bottom. Okay. So we got 1s is our at lowest energy level. Next is 2s. Then we have 2p, which has 3 lines. Okay, we got 3s. We have 3p. We have 4s. And we're going to have 3d. And this has 5. Yes. 4s is going to go first and then 3d. Just go by the order on the periodic table. But just remember, this guy is going to lose it first. Yeah, just something you guys got to memorize. But this is easy because periodic table, just go in line order and it should give you this. Okay. All right, now, if you guys remember, TI, the electron configuration or the noble gas configuration is bracket AR 4s2, 3d2. So honestly, you can just kind of autofill from there. You know that 4s2 is going to have the 2 electrons. And then I'm going to get to 3d in a second, but you can just autofill everything with 2 electrons until then. And don't worry, on your exam for this class, I'm not going to have you guys draw this. Just takes too much time. If anything, I might have you fill out the chart, but you won't have to actually draw the chart. All right, so that's the 4s. Now 3d only has 2 electrons in it, but if you guys notice, there are 5 spaces. So just remember, when you're filling it out and it's an incomplete subshell, you need to separate the electrons. Okay, so this is how you would do 3d. If you did this instead, this would be incorrect. This is not correct, because one of the rules is that the electrons, they like to fill in empty orbitals before they pair up. Okay, so just keep that in mind. Okay. All right, so that is TI. All right, and then if you guys wanted to do TI2+, the configuration is AR3D2, so all you do is just erase these, and it would look like that. That's it. That's what we finished off with last time. All right, any questions on electron configuration, the chart? Hopefully not too bad. I'll be very honest, there's not going to be a lot of questions on the AP test about this. Usually there's about 1 or 2. There might be an FRQ or something where you have to write out the electron configuration, but it's not a lot of points, so don't kill yourself if this is super duper confusing for you. Don't kill yourself to memorize this. There's more important things which we'll go over in Unit 8. Yeah. So TI2+ with the 4s does not have it. Yeah. What's up? No, you don't need to memorize it. They might give you like the wavelength and ask you calculate the energy, but you have the formula for that. Yeah. It's not going to ask you, hey, what are the 4 emissions from hydrogen? You're not going to need to know that. I'll be honest, I don't even know it. Yeah. All right, any other questions? We're about to finish Unit 7. There's one last thing, and it's super duper quick. A lot of you guys are already probably familiar with it. But let me pull up the workbook. Okay, we're going to end by talking about Lewis structures. Okay, so some of you guys might be familiar with this. Now, basically, Lewis structures is an easier way to represent the atom. Okay, if you guys probably noticed this by now, but if we have bigger elements, so for example, if we have something like barium has 6 shells. So if we drew the shell model for everything, we would have to do 3, 4, 5, 6 shells, and then you would have to draw 56 electrons, and we don't have time to do that, right? And no one's going to count 56 electrons, 6 shells, doesn't even fit your paper. And so we draw something called Lewis structures most of the time. And for Lewis structures, what we draw is only the valence electrons, so the outermost electrons. Okay, and this is okay because for the most part, the valence electrons are the ones that do the fun stuff anyway. Those are the ones that connect these elements together to make molecules. They're the ones that move around, that release energy and things like that. And so valence is the one that really matters anyway, okay? So drawing the Lewis structure or just the valence electrons is very, very easy. All you really have to do is count the boxes in that row, okay? So let me talk about what that looks like. So if we pull up our periodic table, we'll do one quick example. Let's say that we are drawing the Lewis structure for, I don't know, fluorine. Let's do fluorine, okay? If we're drawing the Lewis structure for fluorine, I know that it has 2 shells and a total of 9 electrons, right? But for the valence electrons, very simple. All we have to do is count the boxes in that row until we get to fluorine. So fluorine is row 2, but it's box number 1, 2, 3, 4, 5, 6, 7. So fluorine is going to have 7 valence electrons. And that's how you draw Lewis structures. Okay, you just count the boxes in the row and you just draw dots around it. Again, I recommend doing the cardinal directions. It'll make it easier for you to draw and for the grader to see it. But again, you just count the boxes till you get to that element. Okay, let's do another quick example just to make sure we really drill this into our heads. Let's take a look at barium, the really annoying one I just told you about. 6 shells, right? But it's box number 1, 2, and so barium has only 2 valence electrons. Okay, so super easy, a lot easier than drawing the shell models. Again, this is valence electrons, not total electrons. Barium has 56 total electrons, but it's 2 valence. Yeah, what's up? It doesn't matter which direction you put it. I just recommend cardinal direction. So anywhere up, down, left, right, you should be good. Yeah. Yeah, so if you want to do barium like this, that's fine. If you want to do barium like this, that's fine. Whatever. Doesn't. No, don't pair them up. Yeah, you want to separate them because if you pair them up, it has to kind of do with the orbitals. It's just something that chemists do, so don't pair them up. Yeah. What's up? That's only for molecules. Yeah. And we'll get to that, I think, next unit. Okay. There is one thing I do want to mention is what to do with these transition metals, okay? Because this is a little bit different as well. Okay, so let's take a look at something like bromine. Okay, so bromine, if you guys look at the boxes, there's 10 boxes in the middle right here. So you might look at this and be like, hey, there's 17 valence electrons. However, that's not the case. One of the things you need to remember for these valence electrons and Lewis structures is we skip this middle section right here. We skip the transition metals. Okay, and the reason why is because if you guys remember, this is the D subshell, right? And this right here is actually the 3D subshell. Okay, and so we don't count these when we are going or when we're counting the valence electrons. So for bromine, we would count 1, 2, 3, 4, 5, 6, and 7. So bromine has 7 valence electrons. So just keep that in mind. Okay. We skip this middle section when we come to the valence electrons. All right, so that's Lewis structures. Okay, there is one other thing we're going to add on to this, but any questions on this general concept? Okay, a lot of you guys probably learned this in your previous chem classes, how to draw these Lewis structures. A lot easier than drawing the shells. All right, now, it's super duper easy when it's just regular elements. However, we're going to talk about ions now. Okay, so let's take a look at the bromine example, but let's turn it into an ion. Okay, so we're going to do Br minus. Okay, Br minus. All right, now if we take a look at the difference between Br and Br minus, okay, the only difference is 1 electron, right? Now, did Br minus gain an electron or lose an electron? It gained, right? It gained an electron, and that's why it became -1. Just like how if you add a negative person in your life, you become more negative. Same thing here. You gain an electron, which is negative, it becomes more negative. So Br minus's Lewis structure will look pretty much the same. So there's going to be the 7 dots that we had, but since it gained 1 electron, we just draw 1 more on it. And there you go. That's Br minus's Lewis structure. And we just draw the extra dot. God bless you. All right. Any questions on that one? Again, just look at how many electrons it gains. Yeah. If it's, yeah. Yeah, so if it's 2 minus, what would happen is you would actually go to the next shell. So it would only have 1 valence electron. Yeah, because it would jump to the next one. But that Br2 minus cannot exist pretty much. We'll talk about why next unit, so you probably won't get something like that. But I think the next example will kind of answer the question that you have as well. Okay, so let's take a look at the BA example that we were just looking at. So BA had 2 valence electrons, right? Okay, but let's say that we are looking at Ba2 plus. Okay, so now we're looking at a cation. Okay, so we're going to look at a cation. Now, a cation is a positive ion. So instead of gaining electrons, what's going to happen here is you're going to lose 2 electrons. Okay. So let's just think about this. Ba has 2 valence electrons, right? If it loses 2 electrons, it's going to lose the 2 valence electrons. And now it looks like there are no valence electrons, right? However, if you think about the shell model, Ba is right here. Ba had 6 shells, right? So 1, 2, 3, 4, 5, and 6. And the 2 valence electrons were in that outer shell. Okay. So if Ba lost those 2 electrons, this outer shell now is completely empty, right? And so that shell does not exist. So what happens is Ba2 plus, the new valence shell was its old 5th shell. Okay, so this one becomes the new valence shell. And if you look at the 5th shell, there are 1, 2, 3, 4, 5, 6, 7, 8. And so Ba2 plus will have 8 valence electrons. Okay. So if usually this happens with the cation, just keep in mind with cations, if it loses the outer shell, it pretty much turns into the noble gas that it was most similar to. So if you actually drew xenon's Lewis structure, it would have 8 valence. Same thing here. It's going to turn into pretty much xenon. All right, and that's it for Unit 7. I'm going to give you guys 2 Lewis structures to draw, and then we'll finish up. But do you guys have any questions? Do you guys feel pretty comfortable trying this one? Okay. All righty, so let's have you guys try 2 examples. I want you guys to draw the Lewis structures for S2 minus and Li plus. Okay, S2 minus Li plus. I'll give you guys about 2 minutes to try that out. You can check with the person next to you afterwards, and then we'll go over them and then move on to Unit 8. All right, so for S2 minus, we're going to first look at sulfur, and then let's do regular sulfur first and then fix it up from there. Okay, so sulfur has 1, 2, 3, 4, 5, 6 valence electrons. So we're going to draw the 6. Okay, but if you guys notice, it's S2 minus. So we're going to add 2 more electrons. So S2 minus will have 2 extra electrons. So it'll have 8 total valence electrons. Okay, that's it. Yes? Down here? No. Yeah. I'm just doing it just so you guys have clarification. What's up?
If we have to write out a Lewis structure on the test, are they like really particular about like a side?
Like which side you fill in first? Not really, as long as you don't pair up until you have to.
Okay.
Yeah. All right, let's go to lithium now. Now lithium is right here, and it's gonna have one valence electron normally. However, it's positive one, right? So you lose an electron. So lithium loses its electron. And like I told you earlier, for cations, they become pretty much the closest noble gas. So the closest noble gas to lithium is helium, which has two valence electrons. So Li2 plus will have two valence electrons. Okay, so you can draw it like that. And just to clarify, you can draw it like that. You can draw it like this, or whatever combination of those. Okay, the only one I recommend not doing is this, because then it seems like you don't understand that electrons repel each other. So just as long as they're not paired up when they don't have to be. Okay. All right, that's Unit 7. Any questions? Yep. Let's go to Unit 8. Unit 8. So much fun. All right, so Unit 8 is kind of interesting because it could either be really easy or really tough, depending on how well you understand the concept. Okay, so Unit 8, there are, I think, about 3 or 4 really core concepts. If you really understand them well, then it'll be super easy. But if not, it's not going to make a lot of sense. There's a lot of pattern recognition that comes with this unit. So just make sure that you understand the general principles, and it'll help you a lot. Okay, so we're going to talk about valence because we just talked about valence. So let's move on to the actual topic that matters. Okay, so we're going to talk about something called effective nuclear charge. Okay, so I want you guys don't need to write the entire name. It's a mouthful. It's represented by a Z and then a subscript EFF, so effective. So I call it ZEF, just because it's easier to say. So if I ever say ZEF, just know that I'm talking about effective nuclear charge. Okay, and ZEF is a very simple concept. It's basically how strong an electron is connected to the atom. Okay, so how strong of a connection does an electron have with the atom? So ZEF is how strong an electron is connected to the atom. Wow. All right, so to help you guys, I'm gonna draw one of my amazing drawings. That way you guys can visualize what is going on. Okay, so there are a couple interactions, electrical interactions, when it comes to an atom. Okay, so if you guys remember, the middle of the atom is called the nucleus, and the nucleus is positively charged because it's made out of protons and neutrons. Okay, and there are electrons that are flying around it. Okay, and if you guys remember, the electrons are negatively charged, and you guys don't need to draw this drawing. Okay, it's just kind of here just to help you guys out. Okay, so let's just say we have 4 electrons. Now, there are a couple interactions that are going on, okay? Now, if you guys remember, opposites attract when it comes to electrical energy, right? So the electrons are attracted to the positive nucleus, okay? So let's just say that the nucleus is a really pretty girl. So I'm going to draw some hair. And then this electron is a dude, okay? And he's attracted to her, okay? So he's going to try to get closer to her, right? Send her some DMs, try to sit next to her in class, whatever, right? However, she's very attractive, right? And what that means is there will be other dudes that are also attracted to her, right? So this guy's attracted to her, this guy's attracted to her, and this guy's attracted to her, okay? So far, so good? All right, now, all 4 guys are attracted to the nucleus, and they're going to try to get closer, okay? However, when, let's say that these 2 electrons get close to the nucleus, they will inevitably get closer to each other, right? And they're both going for the same girl. So what are they going to do to each other? They're going to push each other away, right? Because they are both negatively charged. So this guy is not going to like this guy, and they're going to push each other away from one another. Okay, so that's kind of the interactions that are going on. The electrons are attracted to the nucleus, but the other electrons push them away from the nucleus. Okay, and that's where the concept of Zeph comes in. It's basically us calculating how strong is an electron connected to the atom, taking into account how attractive the nucleus is and how much repulsion there is between the other electrons. Okay. All right, so we're going to take a look at how to calculate that. It's very simple. Okay. And it's going to be this formula right here. Now, I'll box it for you guys just so that you guys can see it a little bit easier. But Zeph is equal to this right here. It's equal to the nuclear charge minus how many inner shell electrons there are. Okay. It's going to be right here. Zeph is equal to the nuclear charge minus the inner shell electrons. Okay. So a very simple difference equation, just subtract. What's up? No, not innermost, basically anything underneath that electron. So if we're looking, for example, phosphorus right here has 3 shells, right? Inner electrons will be all the ones that are in the first shell and the second shell. Yeah. If it was the 4th shell, it would be 1, 2, and 3, so on and so forth. Just whatever's underneath it. All right, so if we take a look at our phosphorus atom right here, this will be our first example. You guys don't need to write this down or draw it, but if you guys look, phosphorus is number 15 on the periodic table, right? And so that means it's going to have 15 protons, which is why the nuclear charge is 15. So this number is basically just how many protons there are. Now, the inner shell electrons is basically all the shells that are underneath the electron we're looking at. So here we're looking at this electron, the valence electron. Now, if you guys look, valence electron is shell number 3, right? In shell number 2, there are 8 electrons, and shell number 1, there are 2 electrons, and that's where these numbers come in. The 2 is from the first shell, so these are the first shell electrons, and the 8 come from the second shell electrons. Yes. That's correct. Yeah. All right, and so in order to calculate Zeph, all we do is take the 15, the protons, minus the first shell electrons, which is 2, minus the second shell electrons, which is 8, and then you get an answer of positive 5, and that's the value of Zeph. That's the effective nuclear charge. Okay, and the key is written right here. The bigger the Zeph value, the more tightly the electron is held. Okay, yeah. You could, but then that would give you the inner shell electrons. Because phosphorus has 15 protons. The valence electrons is 5. That'll give you 10, which is this. Yeah. So you can use 5, the valence electrons, as the Zeph number. You could do that too. If you just wanted to add up 2 and 8, you can do that. 15 minus 10. You can do that as well. Yeah. But I'm going to show you guys why you don't want to just use the valence electrons. Okay. All right, but any questions on this equation? Okay, so this equation right here has to do, hey guys, this has to do with this, or this 5 value has to do with the valence electrons, right? It's for when you're looking at something in shell number 3. Okay, but let's take a look at an electron from shell number 2, okay? So let's calculate the Zeph for an electron from shell number 2. Okay, the nuclear charge is still 15, right? It's still 15 protons. Okay, but how many inner shell electrons are there if we're looking at a second shell electron? We're looking at an electron in shell number 2. How many inner electrons are there? Yeah, just 2, because there's 2 in the it's for the electrons in the shell underneath. The only shell underneath 2 is 1, so there are only 2 inner shell electrons relative to shell number 2. So it'd be 15 minus 2. And so an electron in the second shell would experience a Zeph of positive 13. So if you look at it, the value is a lot higher. So an electron in the second shell is a lot more tightly held than something in the third shell, which makes sense, right? Because this is a valence electron, a lot easier to get rid of than something on the inside. So that's how Zeph works. It's just comparing how tightly an electron is held by the nucleus. What's up? Yes, it's not always positive. Not a dumb question. Yeah. You mean the first shell? Yeah, it would just be 15 then, because there's nothing underneath. Yeah, those are the ones that are most tightly held. Yes. That's correct. Yeah, and then we just did the second shell. Yeah, so the closer you get to the nucleus, the more tightly the electron is held. Yes.
So we did make a problem about this, like evaluate like how like that low the second.
Yeah, they'll always tell you which one. Exactly. Mm-hmm. Yeah. It would be impossible to do it without knowing. Yeah. All right. Let's do one real quick. Or I'll have you guys do a sample problem, and then we'll move on to the next one. Okay, so I want you guys to calculate the Zeph for carbon and sodium's valence electron. So this is two separate ones, okay? So you're going to look at carbon, and you're going to look at sodium, and I'm going to have you guys calculate the Zeph, the valence electrons. This number, yeah. Alrighty, guys. So I got the answer up there. Carbon has 6 protons. It's 2 shells, and there's 4 in the valence shell and 2 in the inner shell. So 6 minus 2, which gives you a Zeph of 4. And then sodium, 11 protons. There's only 1 electron in the valence shell, and so there's going to be 10 inner electrons. So 11 minus 10, which gives you positive 1. That's it. So that's calculating Zeph. Zeph is just how tightly that electron is being held. And it's the protons minus how many inner electrons.
So like the Zeph value of 1. Average electricity.
Or the average electrical attraction the valence electron experiences. It's how attracted the valence electron is to the nucleus. Yeah, the nucleus. All right, so that's Zeph. Hopefully not too bad. Let's move on to the next one. We're going to talk about something called most common ions. We actually briefly touched on it when we were talking about the Lewis structure of ions. So I'm just going to skip a lot of this and just go to the pattern, okay? Just because this will be most helpful for you. All right, so on the periodic table, we can pretty much figure out there's a pattern to what ion elements want to become, okay? So everybody in this first column, they have a tendency to become an ion with a charge of positive 1. Okay, so hydrogen wants to become H+, lithium wants to be Li+, sodium wants to be Na+, potassium wants to be plus, 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 plus. You kind of get the pattern, right? Basically, everybody here wants to lose one electron. And the reason why is very simple. Let's take a look at Li. Okay, and I'm going to draw the shell model. You guys don't need to draw this. This is just for you guys. Okay, but Li is going to look something like this. Okay. Now, atoms have a tendency they want to have complete valence shells. Okay, and the reason why is because it makes the atom more stable. Okay, if a shell is incomplete, the atom is unstable. And so what an atom wants to do is they either want to gain or they want to lose electrons in order to have a complete outer shell. Now, if you take a look at the outer shell of lithium, it's the second shell, right? And if you guys notice, there are 1, 2, 3, 4, 5, 6, 7, 8 maximum electrons that can go in the second shell, right? It can have a total of 8. Okay, so what lithium can do is it could gain 7 electrons to fill up that valence shell. Or what it could do is it could lose 1 electron, because if it loses 1 electron, that outer shell disappears and now it has it technically has a complete valence shell, right? And so the question is basically, what is easier? Is it easier to gain 7 electrons or lose 1 electron? Again, just looking at the numbers game, they want to lose 1 electron. Okay, it's a lot less work. Yes. Yes, I'm going to get to that in a second. Yeah, great question. Okay. So it's going to you basically want to pick the smaller number. And that's why everybody here, it wants to lose 1 electron. Okay. That's the general concept. All right, so if we apply that concept further, we're going to get to the second column. And everybody in the second column, you can kind of probably already guess what the pattern is. Everybody in the second column wants to become positive 2. Okay. Now, this middle area, the transition metals, these guys have no pattern. It's variable. Okay, and the reason why is because of the D subshell. The D subshell kind of screws things up. And so, for example, if we look at iron, iron can be +4, +3, +2, or +1. There's no real pattern, and you're not really expected to memorize what the most common ions are for these guys. Okay, so just keep that in mind. All right, so we come here. This right here, everybody here is going to be +3. Okay, however, once we come to this area right here, it kind of changes a little bit. And the reason why is because, if you guys remember, there's the metalloids right here, right? And then we have the metals. The ones down here are still metals. And so the MCI pattern really only applies until gallium, okay? So these guys want to be 3, and then indium, and then all these guys, they don't really have a MCI you need to memorize. So just know the pattern only goes to gallium here. Okay, this is the one where it's 4 and 4. And carbon technically wants to become -4 if we're asking about ions, but carbon does something else rather than ionize. Just keep that in mind. Okay, you won't really be asked what's carbon's most common ion, and the pattern really only comes to here as well. This column right here, everyone wants to become -3. So it's 1, 2, 3, -4, -3. And it really only goes to right here. Kind of guess what the next number is. It's -2. Only really goes to selenium. This one is -1. And this right here goes down to iodine. Okay, so there's kind of like a buffer right here. And then these are the noble gases, and these guys are boring. They have no most common ion. They don't want to ionize. They don't want to combine with anything else. These guys are called inert, which means they don't really do anything. Okay, and the reason why is very simple. This whole thing is based on atoms gaining and losing electrons to fill up their shells, right? But if we drew the Lewis structure for example, neon already has a complete shell. Okay, and that's why these noble gases, they don't want to ionize they don't want to combine with other elements is because they're already happy the way they are. They're already fulfilled. All their valence shell is already complete, so they don't want to combine with anything. Okay. Except there's one exception. After krypton, they start kind of ionizing. So just keep that in mind. But again, those are just exceptions. You guys don't really need to know it, or you don't really need to worry too much about the elements down here. Just know the pattern is not ironclad, right? It's just a pattern that we notice. But as we get to the bottom of the periodic table, things kind of change from the patterns that we use in this class. You're not going to be looking at elements down here that often, but just keep that in mind. Xenon can ionize and form bonds. Yeah. No, they're synthetic. Anything past uranium-92 is man-made. They don't occur in nature. And that's why we don't really look at them in this class, because we don't really interact with them very much. No, not inorganic, not so physical. All right, so those are most common ions. Any questions on the pattern? You will be expected to memorize this pattern, by the way. Okay, not the, you don't really need to worry too much about these little exceptions right here, but just know 1, 2, 3, -4, 3, 2, 1. All right, let's move on. So that kind of leads us into one of the main topics for this unit. So we've been kind of just doing the preliminary information. There are about, I think, 4 main types of problems that you need to know for this unit. All right, so the first concept, the main concept, is called electronegativity. Electronegativity. Okay, I like to abbreviate it as EN. So if you want to do that for the purposes of your notes or your homework, I'm okay with that. But once it comes to the AP exam, don't write EN, write electronegativity. Okay. And electronegativity is a measure of how tightly an element holds onto its electrons. So electronegativity is how tightly an element holds onto its electrons. Okay, it's dependent on 3 factors, and these are in order of importance. Okay, so this is an order of priority, and you will be expected to know this. The first is the most common ion. So basically, does it want to gain or lose electrons? Does it want to become negative or positive? Okay, because if an electron wants to gain electrons, if it wants more, it's going to hold on to the electrons it has more tightly. So it's going to be higher electronegativity if it wants to gain. Okay, the second is how many shells does it have? Because the shells tell you the distance the valence electron is from the nucleus. So the further an electron is, the harder it is to hold onto it, right? So the electronegativity will be less depending on how many shells there are. Okay, the last one is how many protons does it have? Okay, because more protons means stronger effect or nuclear energy, positive energy. And so the more protons it has, the more tightly it can hold onto the electrons. But again, these are in terms of priority. So you're going to always look at MCI first, then shells, then protons. Okay, yes. Yeah, you could kind of go down that list. And I'll show you guys how to do them. We'll do a couple practice problems. It's honestly not too bad. It's pretty easy, as long as you remember this order. All right, so let's do part A, okay? Sodium or lithium, which one is more electronegative? Okay, so we're gonna basically go down this list and figure out which one of these holds on to its electrons more tightly. So make sure you guys have your periodic table in front of you, because I'm not gonna have it up on the screen, just so that I want you guys to refer to it, okay? So let's take a look at Na and Li, okay? Which one is more electronegative? So let's take a look at the MCI first, okay? Na versus Li, okay? What's Na's MCI? Yeah, +1. So this one, the MCI is +1. What's lithium's MCI? +1. Okay, so we have a tie here. So we can't use the MCI to determine the electronegativity. All right, so next we move on to the next criteria, which is the number of shells. Okay, how many shells does Na have? 3, it's in the third row. And how many shells does lithium have? 2, good. It's in the second row. All right, so we have a difference here, so now we can use it to determine which one is more electronegative. So if you guys take a look, sodium has 3 shells, lithium has 2. And so lithium, the valence electron is closer, right? So the valence electron is closer to the nucleus because it has 2 shells. And so lithium is going to be more electronegative than sodium. Okay? That's it. You just kind of go down the criteria. Eventually, it'll get pretty second nature. I'm going to teach you guys a pattern to kind of go through this faster. But this will be helpful when the pattern doesn't work perfectly. Okay. All right. Any questions before I give you guys a couple to try on your own? All right. I want you guys to try parts B and C on your own. Okay, part B and C. Which one is more electronegative, fluorine or beryllium? And then compare nitrogen or sulfur. Alrighty, guys, let's go over it. If you guys are finishing up, please feel free to finish. You can just check your answers. But let's go to B and C. So fluorine, MCI is -1. Beryllium is +2. So this would make it pretty easy. It's going to be fluorine because fluorine is trying to gain electrons, right? So it's going to hold on to the ones that it has more tightly. Okay? All right, let's go to nitrogen and sulfur. Nitrogen, MCI is -3. Sulfur is -2. They both want to gain. And so we're going to go to the next criteria. Nitrogen is going to have 2 shells. Sulfur is going to have 3 shells. And so we're going to go with the one that has less shells, which is nitrogen. Okay. So F and N. Yeah, you could think of it that way, but I'm actually going to give you an example in just a second where you can't use that. So just look at the gaining versus losing. Yes.
They're opposite, like maybe one that's stationary.
Yeah, always. That's correct. Yeah. All right, now let me give you guys one. Yeah, did you have a question? Sorry. So the negative and the positive charge matters because it tells you whether it wants to gain or lose, but the value of the negatives isn't going to matter. So -3 versus -2 doesn't matter. And I'm going to show you guys why in a second. So if you guys take a look, let's zoom in. Okay, and these are the ones that'll be the trickiest, okay? Because let's say, for example, we're looking at something like phosphorus and oxygen, okay? So phosphorus is -3, oxygen is -2, right? So phosphorus, if you look, has a bigger number for the negative charge, right? However, oxygen is the one that is actually more electronegative. Anyone want to guess why? Yeah, less shells. There we go. Okay, so just keep that in mind. Doesn't matter what the value of the negative and the positive is. It's about gaining or losing. That's the first criteria. Okay. Always more electronegative. Or not if they're both trying to gain or they're both trying to lose. Yeah, gaining and losing comes first. Yeah, just remember this priority chart. Oh, oops, this wrong one. This one right here. Always go in order. Now, I know it's kind of annoying going through that chart, right? So there is a pattern, okay? And I'm going to show you guys what the pattern is. Okay, so the pattern is as you go up and to the right, you get more electronegative. Okay, and that will help you with like 90% of the problems you get on electronegativity. Just remember, as you go up and to the right, it becomes more electronegative. And then if you're using that, and then there's 2 that are like really close to each other, then you can start breaking it down to the gaining, the shells, and the protons. Yeah. Yes. What's up? MCI is whether it's positive or negative, yeah. So if it wants to become an anion, if it wants to become negative, it means it's going to be more electronegative. Yeah, if you notice, the ones with the negative MCIs, they're the ones that are like up here, right? And so that's why it works the pattern. Okay, we're going to end off by doing one last problem, and these are probably the hardest these problems are going to get. I want you guys to organize these 5 elements in order of least to greatest electronegativity. Okay, and least to greatest means you're going to put the least electronegative ones here and the greatest electronegativity ones on the right, okay? So you're going to, oh, I'm so sorry. All right, so you're going to organize these least to greatest. Give you guys about 2-3 minutes to do that, and then we'll, yes, we'll close with that. Alrighty, guys, let's go over this, and then we'll be all done for today. So we're going to start from the least electronegative and then move on to the greatest. So we're going to start on the left, least electronegative. Okay, there's a very clear least electronegative, right? It's going to be Y because it's on the bottom left. So Y is the least electronegative. Okay, now we're going to move on to this corner right here. Now, if you guys look at this corner, there's phosphorus on the bottom left, and so phosphorus is going to be the next least electronegative. So again, remember the pattern. All right. But these are the ones where it gets a little bit trickier because they're kind of grouped up together. All we do see, though, is that F is the most electronegative because it's on the top right, right? So pattern-wise, you can automatically assume F is going to be the most electronegative. If you guys want to just know, fun fact, F is the most electronegative element. Okay, so we just need to fill in these two. So we got Y done, we got P done, and we got F done. All we have left to compare are N and Cl. So for this one, let's go to, again, the pattern that we learned. So both of these guys want to gain, right? So N and Cl, they both want to gain electrons, so we don't need to worry about that. So we're going to look at the shells. How many shells does nitrogen have? 2. And how many shells does Cl have? 3. And so nitrogen is going to be more electronegative. So our order is this right here. Now, if you didn't know about P, let's just say you wanted to put P in there as well. Okay, so P also wants to gain, and P has 3 shells. The last thing that you need to look at are the protons. P has 15 protons, and Cl has 17 protons. Since Cl has 17 protons, it has more protons in the middle. It's like a prettier girl in the middle, right? They're pulling in the electrons more. And so Cl is more electronegative than P for that reason. It's because of the protons. Yeah.
So say like carrying
So you're only looking at whether it wants to gain or lose. It doesn't matter if it's -3, -2, -1. You're looking at gaining and losing. Because I told you. If it wants to gain or lose, you look at the MCI. If the most common ion is negative, it wants to gain. If it's positive, it wants to lose.